Well, good afternoon. Thank you so much for coming to this AAPT Symposium on Physics Education and Public Policy. This is an annual event that we're just thrilled to support with the AAPT national meetings. I think it's, as you are well aware, we're preaching to the choir here, increasingly important for us to engage. My name is Noah Finkelstein from the University of Colorado Boulder. I will be presider at this symposium. We have two fabulous speakers who I will introduce in a moment. But it's worth taking just a pause as we begin here. We'll have folks rolling in as sessions are just ending. To note in the introduction that it's stated that this session brings together individuals who play pivotal roles in helping to shape policies and who provide information to policymakers. We hope to provide a look at the process of policymaking as well as actions you might take to contribute to the decisions about policies affecting physics and STEM education more broadly. If we don't act, others will. We're thrilled that so many members of this community have stepped up to participate, to shape the national landscape, to shape the state landscapes, the regional landscapes, the international landscapes in physics education and now more broadly in STEM education. I continue to say in just about every venue, these are unprecedented times in STEM education. The level of attention that's being paid and the decisions that are being made now will have dramatic impact for many years to come, and at the bottom line, impact the children in our communities, the students in our classrooms, and honestly, the fabric of our society, how we shape and invest in our own future. So with that, I'm really thrilled. I'm also thrilled that this symposium is supported with memorial funds, and particularly in memory of Mario Iona, who, what a tremendous legacy to leave. Please read about him, the tremendous, actually, obit from his son, and now leader Steve Iona, here, who is an incredible advocate and an incoming or newly anointed president here of AAPT. We're tremendously grateful. Both to the legacy of Mario and to Steve continuing that torch. So thank you, Steve. And then, of course, to the AAPT leadership, Beth Cunningham and Bob Hilborn in particular, as well as the many staff and at the AAPT who make all of this happen here. Not just this meeting, but the work that we do as a community to stand up, advocate, and educate for physics education. So with that, we couldn't have two better speakers to talk about the changing landscape and projections into the future, both nationally and then regionally, and how those two connect in really great ways. So our first speaker is Paula Heron, known very well in the physics education research community, one of the national leads. She's a professor at the University of Washington since 1995, a tremendous researcher in just about all areas of student learning and understanding student reasoning, and you may or may not know, has been a tireless advocate and agent in physics education, serving on a huge number of regional and national boards for physics education, not least among which is the National Academies Commission report, Adapting to a Changing World, that she'll be telling us about. You may or may not know, she may or may not share, that she is one of the architects for even allowing this report to move forward. This was initiated as a decadal study in physics education, and it's through Paula's tireless work that actually got launched, and then she actually was rewarded by being able to write the report and do the study. So please join me in welcoming Professor Heron.
Thanks, Noah. Is this on? Okay, you can hear me? So thank you very much, Noah, for organizing this, for the introduction, and thank you to the members of the AAPT leadership who are putting together this symposium. I want to start with a bit of a disclaimer to say that I'm speaking on behalf of a large number of people who contributed to this report, but some of what I'm going to say basically just reflects my own views, and I hope it'll be easy to distinguish what is the official wisdom of the NRC and what is just my own particular spin. So. I believe there are cards being distributed, so if you have a little colored note card and you want to jot down a question or a comment you might have, Noah is going to curate those, and hopefully that'll provide a little structure for the question and answer portion of the...
Forgive me for not saying this before. So
I have to say I feel sort of like a luminary because I'm blinded by the light out there. But okay, so the report that I'm going to talk about is available for free to download from the NRC website. And much of what it contains in terms of the data, the insights, and the resources were generated by people who are in this room right now or who are at least members of the AAPT. So that kind of posed a problem when I was trying to prepare this talk, because I had to ask myself, well, what about this report is useful to the AAPT membership, given that it contains a lot of stuff that they themselves have generated? And I came up with, well, it's useful as a resource because it pulls together a lot of data, a lot of resources that were previously scattered in a lot of different places on websites and in reports and so forth. It also can be used as a political document to support local action. So this is something that we, the authors of the report, really hope it will be useful for people who are trying to effect change locally, to be able to say, look, here's a national document produced by a committee of the NRC that says this is a good thing for us to be doing as a class, as a department, as a professional society, as a university or whatever. So we really hope it'll be used in that way. I also thought, well, how could a talk about a report be useful to an audience that already knows much of the content of the report? And also, how can a talk about a report that you can download for free and read by yourselves be useful or even perhaps interesting? Well, not everybody who's a member of the AAPT or who is here in attendance would necessarily know that the report finally happened. You've probably been hearing about it for a number of years. Well, it's out there. You can get it either in a beautifully bound, modest paperback or, like I said, downloaded free as a PDF from the NRC website. I'd like to highlight just a few of the findings and recommendations, just really to give you a flavor of what sorts of things you'd find in the report, not to try to comprehensively summarize everything that we discussed or that we found or that we recommend. I want it also to have it serve as an example of something that has a potential for both local and national impact that came from an individual member of our community, Joe Reddish, who took the initiative. I'll say a little bit more about how this happened in order to launch this process that led to this report. So this was really a bottom-up effort, not a top-down effort. Nobody at the national academies was saying, it's about time for us to have a report on undergraduate physics education. The push really came from the grassroots and involved negotiations with both the NSF and the NRC. And as I said, I want to encourage you to use this document for good and not for evil, in order to support what you want to get done in your own institution, to be able to provide support for things when you are interacting with funding agencies, when you're submitting proposals, when you're reviewing proposals, when you are perhaps serving in some other capacity with a funding agency, with Congress, with your local representatives, with your school districts, with your university administration, and so forth. So just by way of an outline for what I'm going to say, I want to talk a little bit about the process, because the process that leads to the generation of reports like this is, unless you've been involved, it's probably somewhat mysterious. And for me, it was fascinating to be involved in it from the very beginning to the end. And so I want to share some of that with you to sort of give you a sense of how these things come about. Also to make a few, like I said, just touch on a few themes and a few of the findings and a few of the recommendations from the report, just more as a flavor than anything else. I will probably leave out many of your favorite topics, and I apologize for that. And talk a little bit about what we found, a little bit about the role of physics education research in this report, and a few selected recommendations, and hopefully leave plenty of time for questions and less time for answers, but plenty of time for questions. So the general NRC report process. So some of the things that I didn't know before going into this is that there are very strict rules and policies about how these sorts of reports, which are going to carry the imprimatur of the National Research Council, how they come to be. So for example, the Federal Advisory Committee Act requires that information gathering meetings of the committee are open to the public. And so the information gathering meetings are advertised. The schedules are available on the web, and they are in principle open to the public. Written materials provided to the committee by individuals are maintained in a public access file. So all of this is meant to be transparent. To my knowledge, it was not broadcast on C-SPAN, but it might have been. And the NRC study committees typically gather information through these open meetings, through the submission of information by outside parties, reviews of the literature, and the investigations of committee members and staff. So the committee contained people with expertise on various different topics, and we carried out our own sort of modest studies, sort of meta studies of certain things. And this is basically the process that we followed. I'll say a little bit more about the process in this particular report. After the information gathering phase, then we deliberate in private. And the point of this is to be able to have free and open discussions that are completely unofficial and to try to develop recommendations free from outside influence. There are summaries of these meetings, but not the whole sort of sausage-making process is not open to the public. The analyses and the drafts go through a stringent peer review process, and the reviewers who are not known to the committee members in advance are publicly acknowledged after the process. And until that peer review process and the reviewers, there's a review body, until they are satisfied that the report authors have satisfied the comments and questions and criticisms of the peer review body, then the report cannot be made public. And I should say that last March, I gave a talk about the report at the APS meeting. And when I boarded the plane in the morning, I didn't know whether the report would be released that day until I touched down in Baltimore and found out that it was in fact public, and I could talk about it at the meeting rather than trying to fill 30 minutes with blathers. So that was a bit of a nail biter, but it's a very strict, very legally well-defined process. The particular report we're talking about, Noah alluded to the fact that at one point it was dreamt of as a decadal study for physics education or physics education research more specifically. So the idea originated, at least as far back, Noah doesn't remember, and I don't remember exactly either, but I know February 2007, wow. So I came on board in 2007, 8-ish, and as Noah did as well, because Joe Reddish decided that it was time for there to be a decadal study, and because these decadal study documents are extremely influential in various other fields of science in helping set direction. So he took the initiative to do this. He got me and Noah involved, and we started drafting some kind of proposal language and a white paper, and there was a process by which Noah and Joe went and talked to people at the National Academy, and then they talked to people at the NSF, and after a long process, you can see that eventually in 2010, the statement of task was agreed to by the governing board. So it was funded, and it first started happening in 2011. So it was a long process, during which point some of us actually forgot that it was happening. And then at that point, the committee was formed. And of the people who had been involved in this process, Joe and Noah and myself, I was the only one who was lucky enough to be selected to serve on the committee and not just have reflected glory. So the context, some of the things that were in the air around the time that this was coming up was that this is well known to everybody here. It's not as well known to the people in the APS audience that I was speaking to last year. The vast majority of students who take undergraduate physics courses take them at the introductory level and take no further physics courses thereafter. 500,000 students take an introductory physics course in any given year. About 20% of those are at two-year colleges. Is that figure correct? Seems low. Anyhow, that's what we published. Must be correct. And of the students who take introductory courses, just 1% will obtain a physics bachelor degree. So this was some of the things that we were thinking about. It's not even, you can't even call it a shrinking pipeline, because what happens between that first year and subsequent years is so drastic. We were also thinking about the relevance of the sorts of courses and programs that we were offering students, undergraduate students in physics. We were talking about the diversifying career paths, how the traditional career path followed by people in mythical generations past, in which they got a bachelor's degree and a PhD and then went on to work in academia, was not the only path available anymore. There were whole new research areas emerging that were not necessarily, which were well represented at something like an APS meeting, but are almost completely absent from an undergraduate curriculum: biological physics, computational physics, and so forth. Research findings about instructional methods were, as has been talked about in a lot of talks at this meeting, were had been for several decades under intense scrutiny and had resulted in a lot of new findings, a lot of new knowledge about how the undergraduate teaching process actually works. And there was a climate in which there were other national reports being prepared, such as we were in parallel for at least part of the time with the National Task Force on Physics Teacher Preparation. The Spin Up and Spin Up TYC reports had been out for a while, and there was also the NRC report on discipline-based education research. So the committee's charge was to produce a report that identifies the goals and challenges facing undergraduate physics education and identifies how best practices for undergraduate physics education can be implemented on a widespread and sustained basis. In so doing, the committee will assess the status of physics education research, PER, and will discuss how PER can assist in accomplishing the goal of improving undergraduate physics education best practices and education policy, and further that the committee's charged to focus attention on students in 3 categories: students in fields such as engineering and life sciences who need a physics background for their vocations, physics majors who typically proceed to graduate school into the workforce, and students who will be teaching physics and physical science in K12. So the fact that the charge even identified that as a really critical segment of the undergraduate physics student population was very encouraging to us. At the same time, there was a national task force going on, and we didn't want to duplicate what they were doing. So the committee membership, you'll recognize many of the names on this list. I do want to single out Mary Beth Monroe for particular recognition. As you know, Mary Beth passed away recently, but as a member of this committee, one of her roles was to represent students in 2-year colleges, which she very ably did, and also was a very strong voice for keeping us focused on students from non-traditional backgrounds who are in undergraduate physics courses and don't look like necessarily the majority of the students we see at the 4-year research universities. So the committee membership was included people who represented professional societies, major research universities, physics departments, education schools, primarily undergraduate institutions, 2-year colleges, and we even had a high school teacher on the committee who helped us keep in mind what happens in that transition from high school to university, and also to help us remain focused on the issue of preparing teachers to go back into the K-12 system. We had some very good staff that I would like to acknowledge, but I want to talk a little bit about the process. So after the several years that led to the formation of the committee, we had 5 committee meetings that were held over this period of time. And in addition to sharing our own expertise and what we had been finding from the literature, we invited a few people to come in and talk to us about the cutting edge of things such as upper division physics education research, the PER User's Guide, and new models for engaging students at the high school. We drafted the report, undrafted, redrafted, de-drafted, drafted again, and then eventually it went out for review, it came back, it was revised several times, and finally published in the summer of 2013. So the themes that were identified were that physics is fundamental and foundational, and that may sound a little bit redundant, but what we meant was that undergraduate physics education provides students with unique skills and ways of thinking that are valuable well beyond physics, and that benefit the students themselves and also have value to society as a whole. So we wanted to emphasize the fact that physics is an important science, as a pillar of higher education. We also identified a lot of causes for concern. So we noted that the familiar college environment is threatened by powerful, rapidly changing external forces that we couldn't even keep up with during the period of time we were writing the report. There were threats to close down entire departments in the state of Texas. There was the sort of tidal wave of MOOCs sweeping over the country. There were people in physics departments being furloughed all over the place. There were all sorts of things happening that are continuing to happen. And to talk about a landscape is a bit of a misnomer, because things are shifting so rapidly that even some of the things in the report now seem sort of quaintly outdated, even though it was less than a year ago. So perhaps the major cause for concern is this rapidly changing external forces. Very difficult to predict what's going on. And so the agility of the physics community and being able to respond to those is something that we really felt was an important theme. Major challenges, so current practices in undergraduate physics education, we concluded, do not serve most students well, and they serve some students extraordinarily well, for most students are not necessarily well served. We also wanted to emphasize that there are many improvements that do exist, many of which have had significant impact on how physics is taught at the undergraduate level, others of which have remained somewhat localized in terms of their impact, but there are a lot of things out there that could be spread to other physics departments and improve physics undergraduate teaching more broadly. And that the one thing that was different when we looked back at reports that had been authored by committees over the last 100 years or so was that we now have this growing field of physics education research that allows us to put many recommendations on a firmer empirical background than has happened at some times in the past. So these themes provide sort of a broad framework, but the report, the meat of the report itself has a couple parts. One is the current status, where you try to assess the current status of undergraduate physics education, both by looking at who are the students and what are they doing, what sort of courses and programs are we offering to them, how are we teaching them. And as I said, the current status was only current for about a day as things kept changing. But I'll show you some things were changing a lot and some things are not changing so much at all. So the students, who are the students that we're teaching was a major focus of the report, just to help all of us, especially those of us who spend our entire careers in one particular type of institution, to recognize the diversity or lack thereof of physics who are studying students who are studying physics in different institutions, or not, as the case may be, enrollment trends in higher education, and to look more specifically at different segments of the physics student population. So enrollment trends. We were and are seeing increases in the overall undergraduate enrollment. The number of students who in the United States who are attending higher education is increasing. The fraction of students who are taking post-secondary education part-time is increasing. Students are getting older. The fraction of students who represent historically underrepresented minorities is growing, and in particular at the two-year colleges. Online enrollment, this was a couple of data points that were kind of surprising to me, is that a third of undergraduates, this is current 2 years ago, I have no idea what the number is now, take at least one course online. And that in 2003, so this is 10 years ago, almost 1 million students were taking a dual credit course in which they were probably on a high school campus taking a course that conveyed college credit as well. So these are some of the factors. This was some of the description of our student body. So you'll see here's the enrollment trend. The number of students studying and getting bachelor's degrees in all the STEM fields is increasing rapidly. Physics, not changing really. You could argue about the dips and valleys there, but I think the striking feature here is the red line goes up and the blue line kind of just moves along. At the same time, the number of students who are taking high school in physics is growing very rapidly, so that we're not seeing a translation of that into the number of students who are taking bachelor's degrees in physics. Students have access to and are successful in a wide variety of careers. You can see here that this is the field of employment for students who got bachelor's degrees in physics and they go into the private sector in engineering, non-STEM related careers, astronomy, computer or information systems, other types of things. So there's a lot of things our students are doing once they graduate that are things that we are not ourselves, typically as university professors, high school teachers, that familiar with. At the same time, some of the things that are not changing so much is the participation of underrepresented groups. So this is the percentage of students who are women and the percentage of students who come from underrepresented minorities. So those things, you could argue about some trends there, but I think that the major point is that some things are changing rapidly in higher education and in physics in particular, and other things are not changing so much. And so one of the tasks for our committee was to try to say which of these are causes for concern, and if they are causes for concern, what might be done about it. So, and also we noted that this is not news to anybody here, is that fewer than 1/4 of U.S. colleges and universities have graduated a student certified to teach physics in the last 2 years, so we're not doing our job preparing people who will be future high school teachers, and that only 1/3 of those teaching physics at the high school level have a major in physics or physics education. So again, physics departments are not really, we're not pulling our weight as far as providing graduates to teach physics. So let me go back to talk a little bit about the educational landscape. So as you can see, I'm kind of cherry picking some of the data, but as I said a couple times, I want to give you a sense of the sorts of things you might find in this report were you to read it cover to cover or skim it. So the educational landscape, we investigated things such as the methods by which physics is being taught, the content and structure of courses and degree programs, the efforts to increase the diversity of the student body, efforts to improve the number and quality of future teachers, assessment of courses and programs and faculty development. And since Noah's telling me I've only got a few minutes left, I will skip even some of the ones that I intended to talk about. But courses and programs, we spent a lot of time talking about this. And there was recently a report, I'm not going to get the name right, but there was a task force of the AAPT that reviewed the undergraduate curriculum. Ernie Behringer was, I think, the leader of this. It's still going on, right? Okay, so I won't anticipate, but they are taking a very in-depth look at the nature of the curriculum and looking at the degree to which it is actually reflective of what physics is today and what physicists do. So we thought this was a very important thing to reflect on and to look at the changes that were happening in other STEM fields that were not being reflected by similar changes in physics. So for example, in biology, we all know that biology is becoming increasingly quantitative. It's a huge growth area. There's a lot of overlap with physics, and we are seeing that this is not reflected in a lot of physics departments. So we talked in the report about updated introductory courses for life science majors, different flavors of physics degrees, new courses for majors that talk about computational physics, for example, biological physics, lots of different double degree tracks, things that make the physics major a more versatile and more up-to-date degree. And the increased emphasis on undergraduate research, which we also thought was something very important to emphasize. So I'm going to skip to some recommendations. Well, let me say a little bit of, one part of the report talks about the growing field of physics education research, what physics education research has done for the improvement of undergraduate physics education, what needs to be done to support PER as an important resource for the physics teaching community, and what needs to be done to support PER as an intellectual, as a scholarly pursuit, independent of its service role for physics education. And so let me just go on to some recommendations. And again, I'm going to cherry pick here a little bit. So the audiences for the recommendations. The report we considered to have a potential impact on a wide variety of people in different offices. Individual physics faculty, department leaderships, academic leadership, so going beyond the physics department or a College of Natural Sciences or wherever you happen to find yourselves. Funding agencies, very important. There's been as you all know, a lot of churn within the National Science Foundation when they're trying to sort of figure out, again, how to best support improving undergraduate science education, recommendations for education researchers and for the professional societies, all things that can be done to try to improve the current situation in physics education. So I'm just going to highlight a few of these. So for higher level academic administrators, one of the, I should say that among the recommendations were to try to set the tone at the top by conveying to faculty in traditional STEM and other departments the importance of improving education, the importance of having a critical view of education, the importance of taking an evidence-based view towards education, to support faculty who conduct discipline-based education research, to establish faculty lines or units in order to foster this sort of activity on their own campuses. This is a sort of recommendation that those of you who are perhaps struggling with your own administrations about the continuation or creation of such lines can use this sort of document, I think, as support for those efforts. For funding agencies, to support a balanced portfolio that includes dissemination of good practices and both applied and foundational education research. So this is something we would like to see from the funding agencies, is to be able to get funding for very speculative research as well as for research that has direct and immediate applications. This has not always been the case, at least for the National Science Foundation, but we think it's important for making sure that physics education research in the future, that there's enough very fundamental investigation of how people learn that will support improvements in classroom teaching down the road that may not be obvious from the get-go. So let's see. I'll just say one more thing about education researchers, that again, to continue research efforts to develop a foundational knowledge base for physics education. Much of the report and much of the discussion in the report about physics education research obviously focuses on it as a means for improving classroom teaching, but we were also very careful to want to support PER as an intellectual pursuit that has a lot to offer in terms of just foundational knowledge of the learning and teaching processes. So I'll stop there by making another plug for you all to go and download this report or order the paperback and to ask questions.